Hey class, this is Mr. Schmidt for December 1 AP Physics class. So last time you had class, you took a test. Notice there's the grade defense template is still available if you got something right. A standard you demonstrated mastery on the last test, you can go back and demonstrate, get points on previous tests. So give me a screenshot of your older one and a screenshot of your newer one, and explain why you get more points. And I'll be happy to award you points onto your older tests. Okay, there's no deadline on that. Whenever you want to see your grade rise, go back and look over those. We'll have one more quiz in December and then the final exam in January, so you can keep studying those points you missed and keep adding to the points you got right. Okay, so today we're talking about gravitational fields and potential energy and work in kinetic energy. So there's going to be a lot to talk about today as we start this new unit on energy. So to start off, it's been a little while. You guys had a nice long break over Thanksgiving, so I thought we'd do our Fermi question. How many bites of food do you take within the last 7 days? Okay, so interestingly, we had questions whether a bite was one time putting something into your mouth, or how many times do you chomp down on a piece of food. That gave us kind of two blocks of numbers for how students answered that. A lot of students said around 1,500 to 2,000 mouthfuls of food based on their research. It's interesting, some people looked up how many pounds of food you eat and how many ounces of food you pick up on a fork, and that did the math that way. Some people looked up how many calories do you eat in a day and how many calories are in each bite. Some people looked up, well, one person was eating breakfast and they counted how many spoons. What just happened here? All right, I don't know what just happened there. I was recording and I hope I'm back. All right, so we had lots of different options for how to do that. Like I said, 1,500 to 2,000 tends to be the number that people got. If you counted how many times you chewed, we got about 10 times more, about 10,000 to 20,000 actual times you chomp on food over 7 days. Okay, remember, we're trying to prepare you for all sorts of things. If you think about students who are sitting in class in 1902, even up to the 1920s and 1930s, flying was just an idea for such a long time. And then in 1903, the Wright brothers started to get some small flights, a few hundred feet for the very first flights. And by 1969, we had a space flight that landed on the moon. Okay, so if we're trying to predict what's going to happen in the next 60 years from today, from 2020, I'm not smart enough to make those predictions. So I'm just going to keep asking you weird questions and push you to think about where you're going to find your evidence, what kind of reasoning are you going to go through, and finally, what claim are you going to make based on those pieces of information. Okay, and then hopefully that's going to prepare you for your college career and life and wherever those points take you. Okay, so kind of a philosophical question. Why does G equal 9.8 meters per second squared? First of all, we can know, how did we find G? You dropped a pumpkin or a bowling ball or whatever you have, and it falls, and you measure the distance and you measure the time, and you back solve D equals 1/2 AT squared. You get, for almost everything you drop, G is very close to 9.8 meters per second squared. So we know it exists. We know it is measured. Anyone can measure it anywhere on the surface of the Earth, and we get very close to the same number. Okay, but in order to really answer not just the how, but the why, we need to start looking at forces, the four fundamental forces, and the fields that they generate. Okay, so we're going to identify the four forces, and then we're going to calculate specifically based around gravity. So this semester is gravitation driven, okay? These other ones are important, and they play a huge role, especially in modern physics. But semester one, we're going to focus a lot on gravity and on mechanics and human scaled events. Okay, so here we see if we have two objects, okay, they are applying a gravitational force on each other. Now, it is 10 to the negative 39th, okay? So 0.038 zeros later, 6, very small number. So when I hold these two objects, I don't feel the force of gravity pulling these two together, but they do. This exerts the force of gravity on this one, and this exerts the force of gravity on the red one, okay? Similarly, Earth is pulling me down with a force of gravity, and I'm pulling the Earth up based on my mass, okay? Now, my mass relative to the Earth is very small, 0.00 times 10 to the negative 39th, very small number, okay? And the farther and farther away I get from the Earth, the less force I will experience based on Earth's gravity, but it still exists. It goes out infinitely, although it decays at a greater rate, okay? So we're going to talk about how we measure that force of gravity over greater and greater distances. Okay, similarly, the sun is applying a force to me as well. The sun is being a massive object, fair distance away. But if the sun did not apply a force of gravity to me, then I would probably be sailing off into space, right? I'm going to be an object in motion, staying in motion in a straight line, unless I have an outside force. Okay, so this is the first force we study. It's also the weakest. Okay, and then the next up, called the weak force, this happens inside an atom, inside specific particles, okay, like neutrons, okay? And then we have different particles that can decay inside an atom. And with those particles, you can then eject an electron through beta decay from inside the nucleus, which contradicts what you may have learned in your introductory to chemistry class, is that nucleus does not contain an electron. Well within the subatomic particles, if you have certain bosons congregate, you can form an electron and it can eject out of the nucleus. But there's weak forces there that hold it all in place and keep an atom relatively stable. Okay, now if a neutrino hits just the right way, things can fall apart. Okay, now there's lots of neutrinos streaming through everything, but they're so tiny and the nucleus is so small, it's very hard to get this hit, which also made it, by the way, very hard to measure. Okay, so we're not going to be going through any particle decays in our study of introduction to physics, but it exists. It's one of the four fundamental forces. Okay, the one we're going to spend a lot of time on second semester is the electromagnetic forces. Okay, so that one, right, if we now have two particles, and let's say I rub one, give it a charge, give this one also a charge, okay, now they have the same charge. As they come close, I should be able to start feeling a repulsion of positive charge to positive charge, as though I've built up a static electromagnetic charge, and it's going to give me an electromagnetic force. Okay, it's going to be much stronger than the force of gravity. Okay, and just like gravity, the farther away they get, the weaker that force is, but it still exists. Okay, and has a great deal to do with the spin of the particles. All right, and by the way, positives and negatives, they are going to attract. Okay, same with magnets and charged particles. Okay, And then the strongest force, called the strong force, is what keeps the inside of an atom together. So we can talk about the individual protons and neutrons and what's holding all those little bits together, okay? The bosons and all those things, okay? Or we can talk about if we have two protons, if we have a helium atom where there are two protons inside the nucleus. Well, electromagnetic force tells us that positive and positive want to repel. What is holding it together? Well, it's a strong force, okay? That proton and proton is being held together with a strong force. Now, if you expose this to a great pressure and force, like a nuclear bomb, or it gets struck by some other piece of radiation, then it can break apart. And when it does that, all the force that was holding it together can be released into energy, okay? Which is going to be true for all of these things. If I have the pen and the earth, and I put some force and I release it, the pen falls, and based on its position, it is going to release energy into the system, okay? So first it was stored energy, and then it becomes kinetic energy, which is exactly what we're about to talk about here. Okay, but that gravitational force, rather than saying for every individual point in space and doing the calculations, what's the force here, what's the force here, what's the force here, and going through every point in space all around every star and planet and sun and black hole, we can start plotting these points and creating a field of plots of different points and what the gravitational force would be at any given position. Okay, so that field will tell us some number has a value for that point of space and time. So as we get more and more massive objects, okay, with more mass, more density, we get more and more gravity, and we can plot that and map that into a field, okay, so a gravitational field. And that can be true for any number of things. We'll also be talking about electromagnetic fields as well, okay, next semester. Okay, but this gives us an introduction to it. And if we wanted to plot those points, we could do that for any object. So it doesn't have to be a black hole or a star. This could be a bowling ball. And that bowling ball is going to look at the gravitational field, and it's going to be attracting objects to it from all directions. Now, if you stand next to a bowling ball, again, remember that it's a very small force. You tend not to see it or experience it. But if you were off in space, or if you have all this carefully suspended from wire, you can actually get some of those objects to start to influence their positions as they stop and overcome the inertia. Okay, so the gravitational field is the force felt by a tiny unit of mass placed at the center. So if we put a mass at any of these places, we know the relative magnitude of the force of gravity in any point in space. Okay, now if we don't want to know the relative force, but we want to know the absolute force, then we can use the universal law of gravitation. Okay, so this is a constant you need to know, a constant you need to have written down in your notebook, hopefully on top of a page where you can easily turn to. Okay, amazingly, at the end of the 1700s, after a whole series of experiments that led up to this, Cavendish was able to use some already existing apparatuses and put it all together and publish it. And he basically did have a bowling ball hanging from a couple wires, and he could measure the torque on those wires and on this apparatus, and he could figure out exactly, given the masses and the distance, what this constant was. And what we know today is it's 6.67 times 10 to the negative 11th, okay? And units are super important here. Newtons, meters squared per kilogram squared. So we need our masses in kilograms, our distance in meters, and that will give us a force in newtons. So it's all going to cancel itself out as long as we follow this. Okay. Now, if we go back to an earlier question of why does G equal 9.8? Well, if you plug in that 6.67 number, big G, and you plug in the mass of Earth, and you plug in the radius of Earth, this whole quantity comes very close to 9.8, okay? Which is why anything on the surface of the Earth, if we drop it, it is in the gravitational field right above the surface of the Earth, and so it is going to experience the same acceleration every time, 9.8. Now, if we go out farther from the surface of the Earth, and now we're on the top of Mount Everest, or we're in the International Space Station, it's going to feel a very different acceleration as we change this radius. Okay? And so if we keep all these constant, we get our 9.8, and we just have to do mass then times acceleration gives us force. But this is really what happens behind the scenes for Newton's second law. All right, so all of that was forces acting within fields, okay? And that set up our position here for today's assignment, which is what happens if I take something and I move it, and now it is at a different position. I have applied a force over a distance, okay? My force is in this direction, my displacement's in this direction. I've done work. Work, by definition, is the change in energy. The easiest way to calculate that is to take the force and multiply it by the displacement that's in the same direction. Okay, so they're parallel to each other. Displacement was this way, force was this way. We can just multiply those two numbers. Okay, you'll see a homework question where force is this way, displacement's this way. We can just multiply those two numbers. If force is one way and displacement's another way, and typical physics question, you're pulling a rope at an angle, but the object's moving horizontally. Now we can just look at what is that angle between the two. We can do force times displacement times the cosine of the angle will give us the work done on the system. Okay, so the work is the change in energy or the force applied over the distance in the same direction. Okay, and it's measured in joules, which is a very important unit of measure. Okay, work is in joules, potential energy is in joules, kinetic energy is in joules, any type of energy is in joules. So we can just move one to another as force changes. So if I do 5 joules of work to lift this object, it now has 5 joules of gravitational potential energy. As it strikes the ground, it imparts 5 joules of kinetic energy right as it's hitting the ground. And then you heard the sound, there is 5 joules of some sort of sonic energy that came out in waves, and we'll cover that at a later date as well. Okay, so potential energy, MGH. By the way, your AP exam often uses U for the variable for potential. I'm going to use PE just to keep it in my mind for right now. Okay, potential energy still in joules, mass in kilograms. As long as we're on the surface of the Earth, we can use that 9.8. Okay, and then we can just do if our force of gravity is this way, then we only need to know our displacement this way. So really what we're doing is our force times our distance, all in the same direction. Okay, so that's what we're finding out when we're doing this potential energy. Okay, then as it hits, we get that 1/2 mv squared. Okay, so that is for an object in motion. If it is falling and it's halfway through its fall, it still has potential based on its height, and it has kinetic based on its motion. So very frequently you'll see a mix of these two things. It has both kinetic and potential. At its start, its journey, before I let go of it, it was pure potential. Whereas it hits the ground, it was pure kinetic. Okay, but anywhere in between, it's going to be a percentage of each one of those. Okay, so again, kinetic is motion and potential is not moving, which gives us our equations. Okay, so it's important to keep track here. Remember when we said force times displacement all in the same direction? Well, those are vector quantities. Those have magnitude and direction. Okay, when we do force times displacement, we get work, which is a scalar quality. Okay, so I can do all sorts of things to get my pen up to a certain position. Once it's in this position, it has a set amount of energy, gravitational potential energy, okay? And then when I let go of it, that force due to gravity is going to bring it down and increase its kinetic energy, okay? And then the sound and the pressure waves are again going to move all over the place as we go back and forth. Okay, so these are kind of the background equations that led us into that 1/2 mv squared and our mgh. Okay, a little SMBC comic for you here. Thanks to this incredible sensitivity, they were later able to use her to detect gravitational waves. And this is the physicist's version of The Princess and the Pea. Okay, and if you get a chance, there has been some pretty amazing innovations in our ability to measure and sense gravitational waves from some very distant objects and events. Okay, so I encourage you to look at that in your own time. All right, so let's finish this off here. You did have an assignment. Okay, so let's take a quick pause. Let's switch over. Okay, so the assignment asked us to rate things like this one right here. Okay, they wanted us to rate the work. Okay, so if we're trying to find work, that's going to be force times the displacement in the same direction. Okay, and of course F equals ma, and A equals the change in V over the change in T, which in this case is our slope. Okay, and D is our area. Okay, so that means if we're looking at this, we can come here and measure our slope, and then also, if we're looking at this, okay, we can also look at the area. So the greater the slope and the greater the area, the greater the work. Okay, now if there's no slope, any number times 0 is going to be 0. If somehow it had a vertical slope, pretty impossible, but in which case the area would be 0 and it wouldn't matter what the slope is. Okay, so when you're doing your ranking, those are the two things you need to look at. Okay, and there was another one that had farther down the line here, dipped below the axes. Okay, so if it's somewhere down here, okay, I think this one was G on their list. Okay, then you're going to have positive area. Okay, but this was also going backwards. Okay, so you're going backwards and you're going forwards. So you'd have to find your net displacement to figure out your net work done. Okay, so keep all of that in mind as you work on this first part. And then the second part was looking at the different moving blocks. And that should also be fairly simple, okay? So if we have the block, we have force going this way, you need to look at the key words here, okay? So if they say it's moving horizontal and force is this way, nice. Force times distance, they're already parallel to each other, okay? Same thing with this one. Okay, that one had that, and then it said upward. All right. So, and it said height. Again, exact same equation. Okay, nice. The only one we had to do a little bit harder was this one right here, where we have an angle, okay? Where it says horizontal, but it also said the force was over here, okay? Now we're going to do force times distance times the cosine of theta, okay? What it's doing is it's taking that vector component of this force, okay? So if we were just looking at if we're just looking at f of x and displacement, okay, notice this is the cosine of theta times f times distance, okay? That would force them into the same direction, okay? So this is just forcing you into your vector components, okay? So hopefully that sets up everything you need for your assignment. Okay, hopefully that set up everything you need for your assignment and you're good to go, and I will see all of you later on.